This is an intro. This is an intro to my calculus video. This is an intro. I have to sing it myself because I don't like ads. Today we're going to be talking about the integration by parts method of integration. And integration by parts is a method that lets us undo the product rule for derivatives. So let's start with that. Let's start by looking at what the product rule for derivatives gives us. So the derivative of f of x times g of x is equal to f times g prime of x plus f prime of x times g of x. Now, we need to get some integrals in here. So if we integrate both sides, that gets rid of the dx, and we're left with just f of x times g of x is equal to the integral of f of x times g prime of x plus the integral of f prime of x times g of x. Now we want to solve for one of these integrals. Let's take the center one, the integral of f of x g prime of x dx. So after a little bit of algebraic manipulation, we arrive at something rather interesting. This says that if I have the integral of a function times the derivative of another, there's actually a way of figuring that out. So let's examine the integral of x times cosine x dx. Well, x, we want to pick a function for f of x such that when we take its derivative, it gets simpler. So we could let x equal f of x on the left-hand side of the boxed function. Okay? Then that would make f prime of x just dx, or 1 times dx. Now, let's assume that g prime of x dx is equal to cosine x dx. Then to get just g of x, which is required on the right-hand side of the function in the boxed formula, I would have to integrate. And the integral of the derivative of g is just g, and the integral of cosine of x is sine x. Now, plugging everything back in, so we have f of x equals x, and g prime of dx was cosine x. So now we have representations for the left-hand side of the equation. On the right side, I simply go through and fill in. F of x was x, g of x is sine of x, minus the integral. F prime is just dx, and g was sine of x. Now this integral is something that I can solve. I know the integral of sine x is negative cosine x, and minus a negative gives me a positive, so the integral of x cosine x dx ends up being just x sine x plus cosine x, plus c, of course. So at the top of my paper, I've written the more formal definition of integration by parts. We usually use u's and v's. So I want to choose something for u to be, and I want to choose something for dv to be. So in this example, let's let u be the natural log of x, and let dv be equal to dx. Now we're going to take the derivative of u and the integral of dv. So the integral, or the derivative of u is du, and the integral of natural log of x is 1 over x dx. The integral of dv is v, and the integral of dx, or the antiderivative of dx, is x. Now we just go back and plug things in. So uv, which is x times the natural log of x, minus the integral of v du. v was x, and du was 1 over x dx. Well, x times 1 over x is just 1, and so this integral just ends up being x. So now you have a formula for the integral of natural log of x. It's x natural log of x minus x. Plus c, of course. Now let's look at something a little bit different. I have the integral of x to the third times e to the x. Now remember, we want to choose u to be something that's going to get simpler when I take its derivative. The derivative of e to the x doesn't change. So let's let x to the third be u. The derivative of x to the third is 3x squared. But when I go to plug that back in, I'm still going to have 3x squared times e to the x. That I'm not going to have gotten anywhere. So there's got to be a faster way to do integration by parts if it needs to be done multiple times. So this particular method is called the lattice method. We choose u and choose dv, and then just use integration by parts multiple times until u disappears. So the derivative of x to the third is 3x squared. The derivative of 3x squared is 6x. The derivative of 6x is 6. And then we integrate dv until we've done it enough times to get down to the end of u. So let's look at what one iteration of integration by parts yields. So we said let's let dv equal e to the x dx. So v is e to the x. And plugging this into my formula, uv minus the integral of v du, we get x to the third e to the x minus the integral of 3x squared e to the x dx. And like I said, we've simplified our formula. We've dropped the degree down by 1, but we still have the product of functions. We can't integrate this right now. So if we used u substitution again, this minus sign in front of the integral is going to make my signs switch back and forth. So let's take that into account and alternate my signs. Now, by kind of connecting these diagonal rows, we can get my final answer after it's that 1, 2, 3 iterations of integration by parts. The idea here is that we are able to do multiple iterations of integration by parts without having to actually write out all the steps. This lattice method makes this very simple and compact. In this example, neither e to the x nor cosine x is going to disappear. So let's see what happens. Let's let u equal e to the x and let dv equal cosine x dx. The derivative of u is e to the x dx, and the integral of dv is v, and we get sine of x. Now plugging that into my formula, we're again uv minus the integral of v du. So we haven't got an integral that I can yet solve, so let's do integration by parts again. So again, we'll let u be e to the x and dv equal, in this case, sine x dx. Integrate dv to get negative cosine x, and derive u to get e to the x dx. Again, with uv minus the integral of v du, let's go ahead and plug in to my formula. And now that we have that, let's try to simplify this out, and remember that what we're trying to solve here is the integral of e to the x times cosine dx. So really what we've said so far is that the integral of e to the x cosine dx is equal to what we have above. But hey, look. The integral of e to the x cosine x dx has now shown up twice in this equation. Let me move my paper up slightly. So if I were to add this integral to the other side, it'd be like adding the same thing to itself, which means we have 2 of that. So 2 times the integral of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x. Now, simply divide by 2. And what we were trying to solve for initially, the integral of e to the x cosine x dx, we find is just e to the x sine x plus e to the x cosine x, all divided by 2. Thanks for watching my calculus video. Plus, see you next time.